into an object that we can call a trans-series, just because it's going beyond standard power series, which looks like that. So in here, the n equals 0, f0 would be the perturbative function, or the perturbative series, if you want, that I started off with. And then I include extra terms, which will be instanton-like terms. So here, A is an instanton action, and then I'll be doing, around the nth instanton sector, I would be doing perturbation theory. This would be G loop amplitudes computed around the nth instanton sector. Beta is just some characteristic exponent. And then when I put all these things together, what I find here is a sort of a double perturbative expansion. Not only the standard power series, one over Z appears, each of these guys here will have a power series in 1 over Z included, but I also have iterating, I'm sort of doing perturbation with this object, with this non-analytic object, which appears here raised to the nth power in order to incorporate the nth instanton sector. Sigma, this number, or this parameter that appears here, is the trans-series parameter. It's essentially counting instanton numbers. But when I'm using this sort of constructions to solve a differential equation, it sort of parameterizes boundary conditions. If I'm trying to solve these objects to solve for an integral, it parameterizes contours of integrations, and so on. You can think of it in many different ways. Now, if you have some nonlinear system, some nonlinear equation, nonlinear integral, whatever that you want to solve, you just plug these answers, and you iterate, and eventually you can compute all these objects here that will build up the trans-series for you. That's very nice, but there's something even nicer about these trans-series, is that these objects are often called resurgent. What does that mean? That means that different instanton sectors at different loop levels, they're related to each other in a very intricate way, which in particular will tell you that if I know one sector, I may know any other or all others, and in particular, if I know the full perturbative sector, I can extract the full non-perturbative data out of it. So somehow perturbation theory already has included in it, well, even though it's a little bit hidden and you have to dig it out, all non-perturbative data associated with the theory you're studying. Let me make this a little bit more explicit what this resurgence means. It means the following. So let's consider that I have a system with some instanton action A, Borel singularities will be located at the different nth instanton locations on the Borel plane. And generically, this is a very general statement for very general classes of functions. Borel singularities lead to logarithmic branch cuts, which look like that. So let me explain what I have here. So I'm just plugging, I'm using just the power series here. They're all asymptotic for all instanton sectors, and I'm calling them capital phi in this way. Okay? And then if all these guys, these capital phi's, are asymptotic, they will all have Borel singularities. And the Borel singularity of the n instanton sector at the kth singularity will have a logarithmic branch cut whose coefficient in front will be a number, we'll get to this number later, but makes appear the Borel transform of the nth plus k sector. So we can see that at the kth singularity of the n instanton sector, one finds the resurgence of the nth plus k instanton sector. So if I'm just looking at different singularities of a fixed sector, I will see all others hidden in there. The coefficient that appears here, these numbers, are known as Stokes constants. This is sort of the hard part of the problem because the structure is already all included in this singular structure. Computing the Stokes constants is a hard problem. They're generic, they're transcendental numbers in nonlinear problems which are hard to compute. They play, of course, the role of making Stokes phenomenon occur. Stokes phenomenon occurs here very simply by what we can say, quote-unquote, chum of the trans-series parameters. So notice that if I go here to my trans-series and I just think about the first two terms, that's the perturbative series, F0, and then at order 1 I have some exponentially suppressed stuff. And if I start off with sigma equals 0, all I have is the perturbative power series, but if there's a jump of the trans-series parameter by the Stokes constant, it jumps from 0 to the Stokes constant, that means that it's turning on, let's say, the first exponentially suppressed stuff, and that's just classical Stokes phenomenon. So if we have this structure, we can just abstract the singular structure that I've shown you here. We can just abstract and think of just some combinatorics which is associated to transeries. So you can think of a chain, the transeries is a chain, which at different nodes will have a perturbative series. They could be the standard, let's say, perturbative series, or perturbative series associated to each of the different instanton sectors. And I can just move around by making use of this structure of Borel singularities. And you find all these combinatorics, I'm not going to show you how, but all these combinatorics with many formulae that can be used later on. In particular, they can give you a lot of information about asymptotics. So let's see some more down-to-earth formulae. So if using these combinatorics and these researches, it is possible to show that very generically for systems which have a single instanton action, the asymptotic expansion of the, let's say, the perturbative sector is given by some formula. Here's a closed form expression, but let's just look here at the one below, which is just the expansion to first order. You can see that it's given by the factorial here growth. Then there's an instanton action to the power g. There's an overall coefficient, which is the Stokes constant. And then I have the one instanton sector, the contribution of one loop by two loops, and so on. And then I have also exponentially suppressed stuff. Like here, the two instanton guy is suppressed as to the minus g, and then the two instanton sector, one loop, two loops, and so on. So if you want a picture of this formula, it's just telling you that if I know multi-instanton data, I can predict the asymptotics of the growth of the coefficients in the perturbative series to arbitrary accuracy. But while we usually make use of these green arrows in the direction of predicting, we should, in fact, also see that these green arrows can work in the other direction and allow us to decode. And that's what I mean by extracting non-perturbative physics out of the perturbative series, is that if I am given all these coefficients of some perturbative power series that I'm studying, and I decompose it in its 1 over g powers and its exponential of something to the minus g powers, then I can extract order by order all non-perturbative information just by inverting the direction of these arrows. These formula are very general. Not only can we use them to the perturbative series, we can also use them for all instanton sectors. Here's the formula, what it looks like for the nth instanton sector. It's a little bit intricate, perhaps it's not very much worth going through all the details, except to say that pictorially, it looks like the perturbative series, because all the forward guys are contributing basically in the same way. The only difference, if you're paying attention to the formula, is that I have a binomial coefficient in front. Everything else is essentially the same. But there's also contribution from the previous guys, the guys that were before. This is not an infinite series anymore. There's just a finite number of guys behind. They will also contribute. They contribute with more complicated combinatorial factors which are associated to sums of repetitions, but they're also there. Here in the formula, just the first term is just associated to the Stokes coefficient of having one step back in this chain. Now, you can have more general stuff because you can have systems where there's more than one instanton action. Here's an example where there's two instanton actions, plus A and minus A, which might look a little bit odd at first, but I will come back to why this is important in a couple of slides. And here's the closed form expression. Let's not worry about that. Let's just look again at the leading contributions which are here in the last line. And you can see that if I just cover the second part, the first part would look just like the one I wrote before. And you see it has an A and has a coefficient, Stokes coefficient, and so on. And then the second part here has a minus A to the power g. And in many systems, it turns out that there's relations between the Stokes coefficient and the one instanton, let's say the 1/0 instanton and the 0/1 instanton, such that when you plug things in the computer, you can tell whether there's just one singularity or two singularities, because the -1 factor either tells you that you see this dot, 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 dot coming out of this asymptotic series, or you see something oscillating, dot and dot, dot and dot. And so, by playing with this kind of formulae, even if you don't really know what is the non-perturbative structure of your theory, just by looking at the asymptotics of the perturbative series, you can extract a lot of information of where you find instanton or renormalon or other types of singularities on the Borel plane. The picture, of course, now is that I have contributions coming from A and minus A, and again, I can just try to unravel this in the other direction and use the perturbative series to decode everybody else. There's also formulae for arbitrary instanton sectors, which I'm not showing you. You can look up in one of our papers. They're, again, quite interesting. So that's kind of the idea of what these methods of trans-series and resurgence are. So basically, you start off with a nonlinear problem. You try to set up your trans-series. These systems are usually, if you're going to do large N duality or large N gauge theory or string theory or whatever, it's hard to show rigorously that what you have to deal with is a resurgence function, and then you use these tests with asymptotics to actually verify or try to validate that in fact resurgence is at work, and then use the trans-series to try to extract information. So let's see how to do that in the large N expansion. So I just want to try to understand the resurgent properties of the large N expansion. So the simplest way to do that is just to try to wash away any issues that can arise from renormalization, and thus will focus on matrix models. And here's an Hermitian one matrix model. This is the partition function. I'm just normalizing it by the volume of the gauge group, and then I'm integrating the matrices with some potential and some coupling, which is the string coupling when you play large N duality. Now, very well known since many, many years that in the large N limit, where this combination GS times N get cost coupling is fixed, the free energy has a perturbative genus expansion, which looks like that. That would be the free energy associated with this matrix model. And these coefficients, which are now functions, and not just numbers, they're functions of the cost coupling, they grow as the G factorial, shown by Schenker in 92 or something like that. So we have to deal with this asymptotic series in this game, and we'd like to know if, this perturbative series has zero radius of convergence. We'd like to know if you can associate a trans-series to it and try to extract non-perturbative information out of this system. Well, the answer is yes, and let me try to show you how to do it. So one thing is that you have to decide on a saddle point of the matrix model to do where you construct perturbation theory, where you construct this series around. And for the quartic matrix model, which is sort of the simplest, non-trivial example that you can use, generically, saddle points, there will be 3 critical points of the potential. Eigenvalues can cluster around each of these critical points, and so you would have some sort of spectral curve associated to the distribution of eigenvalues with 3 cuts. This is generically a hard configuration to write down, but there's 2 simpler sort of Z2 symmetric configurations that you can write down, sort of a 1-cut solution where you just take the quartic potential and just put eigenvalues at the bottom of the well, or a symmetric 2-cut solution where you just have 2 wells and you just fill 2 of them symmetrically. And these are the simplest saddle points to do perturbation theory around, and those are the ones that we've studied. Now, what's the solution to the system? I'm going to give you the details of how we compute to this. I'm just going to tell you basically the solution. The solution will be a solution to a finite difference nonlinear equation, which is known as a string equation. Now you can ask, where does this come from? Very briefly, one way to solve these partition functions is to use orthogonal polynomials. Orthogonal polynomials, they're defined via some recursion coefficients that tell you how to compute the next one given the previous one, and basically they satisfy for different potentials. You'll have different orthogonal polynomials which are associated with different recursions, and basically what I've written here is the continuous version of the recursion relation that tells what are the recursion coefficients that generate orthogonal polynomials for you. Now this is a nonlinear equation. You can try to solve it with a trans-series, and the result is that you find that there are in fact 2 instanton actions, plus A and minus A. Thus, the previous example that I've shown you on how you can have sort of, let's say, completely forward and completely backward instanton singularities on the Borel plane when you have instanton actions A and minus A, and the trans-series looks like an object like this, where all these things are computable. Not analytically, but computationally. So, if all this sort of setup is working fine, this should be a completely non-perturbative solution that would allow us to go anywhere on the phase diagram of the series at large n via Stokes transition. So let me show you that we've done extensive resurgence checks of the large order data associated with this. Let me show you one of those tests in a simplified version of the quartic matrix model, which is its double scaling limit. So I can take a limit where the Duff coupling, which here I wrote as x, I'm not sure why it should be a t, where t is just tuned to a critical value where this finite difference equation sort of simplifies to a differential equation. This is a very famous differential equation that was written down probably 110 years ago by Ponlevet. That's the Ponlevet-1 equation. And so the u now is the double scaling limit of r, of those coefficients there. And this is a nonlinear second-order differential equation. It has a perturbative solution. You can just plug this back into the Ponlevet equation and extract the coefficients. The coefficients, the first few look like that, and they grow as 2g factorial. So they have the standard string theoretical factorial growths. Now it's easy to see why there are two instanton actions. The reason why there are two instanton actions is that this is a second-order differential equation, and in fact, it turns out that if you just plug the answers, it's sort of symmetric. It has symmetric roots. There's the plus a and the minus a. And when you try to solve this using trans series, you find that the solution looks like that. So here we're using G string is the Z of Ponlevet, but we've written it back with G string. And so you see that it looks very much like the equation I wrote before. There are some logarithmic contributions and some exponential contributions. So what we mean to test this and to check whether this solution is in fact resurgent means to use this large order formula, let's say an asymptotic formula. Let me just grab one of those. Something like that, where you're trying to use instanton data to predict the value of this guy. But because in the Ponlevet equation, you can plug these guys here and recursively obtain all these, by the way, rational numbers. You can just try to check whether things are consistent or not. And notice just one more thing in one of these plots is that, let's just grab a random one. See here. There's factors of pi, and these guys are also irrational. So you're sort of trying to use irrational numbers mixed with non-perturbative instanton data to predict a rational number. You can check how good you can do it or not. And here's the plot of how good you can predict stuff, which is here. So you go up to genus 30, so the perturbative guy goes up to genus 30, and then you try to predict it using instantons. And you can see here that the more instantons you plug in, the more correct decimal places you get on predicting this rational number. And in particular, at genus 30 with 6 instantons, you get a result which is correct up to 60 decimal places. So this is very strong numerical evidence that in fact these functions that we're studying are resurgent and that we can play with them. One thing, of course, that plays a role in this calculation are the Stokes constants, which I mentioned before, which are hard numbers to compute. So far in this problem, only one Stokes constant is possible to compute analytically. In fact, this is sort of an easy one. It was computed many years ago in 91 by François David, which is that number. And all others that we have had to use in this problem, here's a few of them, we had to compute numerically. And we don't actually know of a way to predict them analytically. I mean, some of them are not hard to guess. I guess all of you probably can guess what should be the analytic expression for this one. But the other ones, it turned out to be, as far as we can tell, transcendental numbers for which we don't have a good guess. Now, why would this be important is because there's a physical consideration behind these numbers, which is the following. So remember that the Ponlevet series looked like that. So it has all these sectors here, the phi and m k's. And what properties do they have? Well, when n, the nm sectors, when n is different from m, they have generic plane expansion in G string, which means that they're associated to some sort of open string sector. When n is equal to n, we have an expansion in G string squared. There in particular are no logs. Also, the n/0 and the 0/n sectors have no logs. The log sectors are not independent. They sort of all iterate in a simple factor up to the first. Now the physical instanton series, these n/zeros, these guys here, you can compute them, and that's the reason why this Stokes constant is computable as these amplitudes of ZZ branes in this background. But we do not have a similar brane interpretation for the generalized instanton series, so that problem is still open. And that should be, such a physical interpretation should be what would allow us to compute all these numbers as amplitudes in some string theory. Anyways, except for the fact that we don't have those numbers, we do have the trans series set up, so we can start using resummation of the trans series to obtain numerical results for Ponyville solutions at any point in the complex plane, or for the quartic matrix model, again at any point, at finite n, if you want. So in the last 5 or 10 minutes, let me just show you a couple of plots on how to get these things. So this is pictures of the one-cut solution. Here's the one-cut solution for the quartic matrix model, and of the two-cut solution. It doesn't really matter what the pictures are. They're just, the positivity of the potential. These brown regions is where the potential is positive, the blue regions where it's negative. And so if you want to devise a spectral network for doing integration, basically you have filters that start at infinity and at infinity without getting wet. So they cross from dry land to dry land through bridges and cuts. And now, you can compute instanton actions here as B cycles in these geometries. And so Stokes lines will be given by this condition, where this A is computable as a cycle, and then the Stokes lines, which will be associated with phase boundaries. So the Stokes lines are essentially where the trans-series parameters jump, and they grab something else which was exponentially suppressed and we didn't really care about. And then we go around in the complex plane, they start growing, when we hit an anti-Stokes line, where what was previously exponentially suppressed is now of the same order of the initial perturbative data, and then can induce a phase transition. And here's a plot of the phase diagram of the quartic matrix model at complex Etoft coupling. So this is the complex Etoft plane. And what we have here one region. That's the region where basically I have the one-cut solution, and the two-cut solution is here, wrong direction, is here in this second lobe, which is the S2. There are some critical points here. This is where I have the double scaling limit to Ponyville 1. That's where I have the double scaling limit to Ponyville 2. Now, these phases, the one-cut and the two-cut phases, we call them as Stokes phases because they have the standard 1 over n, or to be more precise, 1 over n squared perturbative expansion alongside the exponential of minus n instanton corrections. But as soon as we move into the blue regions, these are regions where basically it has 3 cuts turned on. Now, all eigenvalues, the reason for this is that they all became, they're all organized at the same energy, so they can all shuffle around the cut that they want, and it's no longer true that you have a 1 over n expansion. In fact, you do not have it. You will find oscillatory asymptotics in n, given by theta functions. So in particular, from the standard Lackner-Foster construction of associating a closed string dual in some specific Labial geometry to these matrix models, there will be no clear string dual right now. What you will have is a fluctuation over geometries, which basically they will weight the same, even at first order in perturbation. And things get a little bit worse, well, from this point of view, if you want, it's not necessarily worse. Once you move away from this blue region into this gray region, the gray region is in fact the generic region because it's the one that goes all the way up to infinity, infinitely strong Etoft coupling. Eigenvalues will now, here's a numerical example where 75 eigenvalues at Etoft coupling 5. This is the complex plane where I can find zeros of the orthogonal polynomials or eigenvalues, and they organize themselves in trivalent regions, which have even more intricate theta function asymptotics. So how can we understand analytically these regions? We can use resummation methods to rewrite our trans series. And one thing that we can do is that we can, instead of, so you see, we have the sum over instanton numbers, and then a perturbative series here, which is asymptotic. We can invert these sums and do first the sum over instanton numbers. In mathematics, this is known as transasymptotics. And it's very interesting because if it's variable, which includes basically the instanton non-analytic term, the trans series now looks like what I have written here. I will finish in a minute. looks like what I have written here, where these functions are now convergent. In particular, for polynomial 1, the first, the order 0 function is a Weierstrass elliptic function. And once you do this, it's quite impressive, because you can now find all polynomial solutions from the trans series. So here's a plot of polynomial solutions, and the white dots are the famous poles of the polynomial 1. And there's, as classified by Boutreau, there's different types, truncated, in general, depending on regions. There's this five-fold symmetry of polynomial regions where I find poles, and you see that you start with the truncated, which is a perturbative solution. Just the perturbative series is enough. You obtain truncated solutions where you turn on one parameter trans series, and you have to go to the full two-parameter trans series in order to see all these poles. Now, poles of the solutions are zeros of the partition function, and you can actually do, and I will end with this, you can actually do the same analysis for the quartic partition function, and this is, let me just show you back the analytic plot. This is a region here where we've done a numerical analysis where we're moving away from the 1 or 2 cut regions where you have sort of classical geometries and moving into a region where you should have fluctuating geometries, and those will be the numerical zeros of the partition function, which can also be computed analytically by using the trans series. But I'm afraid my time is up, and so I won't be able to tell you more about that. Thank you very much.
Questions or comments? Johnson?
Just very naively, this can apply to, is it suitable to apply this to standard model or QCD, and what would happen there?
Right, so you can play the game there as well, but it's harder because you have a renormalization scale. So the saddle points are sort of fluctuating depending on where you choose your mass scale or whatever. But in fact, you can find similar things. Of course, here most of the time, I've been focused on instantons because they're associated with Liebrands. That's the thing that happens. In those cases, renormalons would be the things that would play a role. They're a little bit harder to deal with than instantons because instantons have very simple semi-classical descriptions. Renormalons, it's a bit harder to play that game. So, but in principle, modules and complications of renormalization and the semi-classical descriptions of renormalons, things should go through as well.
What kind of physical impact would that give to our the understanding of the physics at a low energy level?
I have never studied, so I don't know what the implications would be, but the naive guess would be that because of all the structures that you can find of this type, is that there will be regions once you go to the complex space of parameters where there will be phase transitions to different vacuum of the theory.
Does your method apply to other random matches and some more like unitary?
Yes, definitely. We have studied different matrix models and also string theory that I didn't have time to talk about. So, I mean, as long as there's no renormalization, it's actually quite easy to play the game.
Okay, we have to move on. Let's thank Ricardo again.